Okay guys, this is a video about inverse functions. So there are different ways to approach inverse functions in terms of questions. I'm focusing in this video on how to find the rule and the domain of an inverse function. And also how to restrict domains to make sure they exist. So remember, an inverse is a reflection around the line y equals x. We're very familiar with reflections around the x-axis. Flips it down, let's put a negative in front of the graph. So that's when you have negative f of x, reflects it downwards. We're also quite familiar with a reflection around the y-axis, which is where you would have f of negative x, like that, in a graph, and that flips it around this way. But when we have an inverse, we're going around a different mirror. The mirror is actually the line y equals x coming through here. And what it allows us to do is essentially you swap the x and y values. So if I have a y-intercept there, in the inverse, this is reflected down and becomes an x-intercept, and vice versa. An x-intercept will become a y-intercept around this line in the inverse. And what we're doing with functions isn't just taking a single point, but taking the entire set of points that makes up that function. So if I have a quadratic, a parabola that we know, something like that, let's do that. It's a little bit wide, don't tell your maths teachers at home. That's a little bit wide at the bottom. That is my parabola. When I put that in the inverse, its x-intercepts become y-intercepts. So there's two of them, there's gonna be one there-ish and one there-ish. And this y-intercept becomes an x-intercept down there. And we end up with the graph looking something like this. Not quite right, but it's not too bad. What you will notice is now I've drawn a sideways parabola, but that thing is not a function. That is a relation because it does not pass the vertical line test. Remember, for it to be a function, it must pass the vertical line test by crossing only once. So we have a problem. Every single inverse, so every single graph has an inverse, but not all of those inverses end up being functions. So what we find is that only functions that are one-to-one will have inverses that are functions. So one-to-one functions end up giving one-to-one inverse functions. Any other case does not give you an inverse function. So if you have a many-to-one function, like a parabola, you will not get an inverse function. You'll have a relation, but not a function. So you have to make sure that when you're dealing with functions that you pass the vertical line tests with the inverse. To find the rule for an inverse function, essentially all we do is we swap x and y values. So the x and y values are flipped around, and then we solve for y. A bit of notation is that f negative 1 means it's the inverse of the original function f. This is not like our index law where you have 1 over x. That's not what it means. What our f negative 1 means is more like our inverse sign. It's an undoing an operation. It's an undoing of something as opposed to applying an index law. Given that x and y values are swapping in the inverse, that also means your range and your domain swaps. So the domain of the original, which is a set of all the x values, becomes the range in the inverse, which is all the y values now. And the range of the original, the set of y values in the original, all become the set of x values in the domain of the inverse function, sorry. Now, in terms of how you answer questions, if it just asks you for the rule for the inverse, just writing f negative 1 of x equals whatever the rule is sufficient. But if it asks you for the inverse function, or if it just says determine f negative 1 of x, then the rule and domain is required, and we'll see that in a second. Just a little side note at the end, we can do composite functions with these things. If I take the inverse and I substitute it into the original, or if I take the original one and substitute it into the inverse, in both cases, I'll end up with x. These are inverses. Inverse operations undo each other, remember? If you're having a plus, x plus 3 equals 5, you subtract from each one. The plus 3 and the minus 3 are inverse operations of each other, the plus minus, they will cancel out. Same thing here. You'll end up with the x on the left-hand side there. Same's happening here. So let's have a go how to do this. Have a go at finding our rules. So first thing I'm going to do is I'm going to write in the inverse, we're going to swap x and y. Swap x and y. That's after I'm going to let y equal f of x, because I don't want to have f of x floating around. It's much easier to have y in there. So I would normally make that y now, so y equals, and then I'm going to swap the x and the y values. So you're going to have x equals 3, y minus 2 squared plus 2. This is simple enough to transpose by hand, so we're going to do that. You subtract the 2, and then you're dividing by that 3 to give you this. To get the y minus 2 by himself now, we're going to square root. Now when you take a square root, don't forget you have a plus and a minus option, which we'll discuss in a minute. And then we add 2. Now you might notice that plus and the minus should cause a problem, because plus do this with a square root graph, and minus does this for a square root graph. They'll be starting at the same place, but one goes up, one goes down. And notice if I plot both at the same time, it gives me a problem that does not pass the function test. So that will not be a function. So what we need to do is decide which one of these do I keep. Otherwise, we can't have an inverse function. The question is telling me I can find one, but as it is, I can't. So what I need to do is go back to the original set of values. In the original values, the original equation, I should say, we had a quadratic with a turning point of 2 and 2. Remember, the x value is 2 there, the y values are 2 there, and it's doing this. But notice we have a domain at the end. It's not telling me to do an inverse of the whole thing. When I do my algebra here, it just does an inverse of the whole thing and doesn't have anything to do with the domain. The domain doesn't come up at all in the inverse function in terms of our transposing. But when I'm sketching it and having the final result, I actually need to take account of the original domain. So I'm going to click and remove that half, because that's the bit it's asked me to reflect. So it's only one half of the graph, not the whole thing. So let's find out, plus or minus, which one we keep. To do that, we need to remember what we said about range and domain. So the domain of the original was x is bigger than or equal to 2, which means the range of the inverse is y is bigger than or equal to 2. So the range has to be bigger than or equal to 2. Let's look at this down here. Which one of these two options is going to make sure I always get bigger than or equal to 2? Well, of course, it's going to be the plus one. If I start with 2 and I add any number to it, it makes it bigger than 2, doesn't it? But if I have 2 and subtract something, it always makes it smaller. So therefore, we only have the positive option. So I can say, therefore, f negative 1 of x equals 2 plus that square root. But that wouldn't be enough. I need the domain because it asked me to determine the function. Now remember, the domain of your inverse was equal to the range of the original. So how do we find the range of a quadratic? Well, let's go back to the start. Let's label our turning point of 2, 2. So the range of the original one is 2 to infinity. So it happened to be y is bigger than or equal to 2, which means the domain of the inverse must be bigger than or equal to 2. And we end up with that. There's the rule on the domain. You could write it in function notation if you want, which would be like this. You have the label, you have the domain, you have the codomain, which we just leave as real values. Remember, the y values are a subset, the range is a subset of that, and then we write our rule at the end like that. Either of those options will be valid. Let's do that again, but this time let's use logarithms and exponentials. And for this, we need to remember that a to the x equals y can be written as log base a of y. This is these are equivalent expressions for logarithms and is what we're going to need for our inverse with logs. So again, first thing, we're going to have in the inverse, we're going to swap x and y. And at the same time, we're going to let y equal g of x and remove g of x from the equation and put y equals in there like that. We're going to have y equals, and then we're going to swap the x and the y. So we have x equals 1/3 log base e, which I could have written as ln. That'd be valid. Just have it for writing base e, I think. Minus 1. And then I transpose to get y by itself. So first thing is multiply by 3. Or divide by 1/3, it's the same thing. Now I'm going to use this fact over here. So I have x equals, I want to write it as the power. So the piece inside the logarithm is by itself now. The base of the exponential is the same base as the logarithm. And the power is what was on the other side by itself. And now I transpose, I add 1, and I divide it by 2. And there's the rule for the inverse. So I can say, therefore, g negative 1 of x is going to be equal to 1/2 plus 1/2, whoops, e to the 3x. I could have left it as e to the 3x over 2. That's fine. And if I want to write it with the function notation, I would do this. Whoops, we don't know my domain yet. I'll get there in a second. You have all of this. And to finish it off, we need the domain because it's asked to find the function. All right, so remember, to find domain, you need to know the original range. We have a logarithm. The graph is not restricted. Remember, logarithm has to be greater than 0 in there. If I solve that, I get x is 1/2, bigger than 1/2. So I have a maximal domain for a logarithm. That's a video for another time, I guess. Which means I have a maximal range. And a range of a logarithmic graph, g of x, is all real values. So that means the domain of the inverse, g negative 1, is all real values. So I can put a little comma at the end, say all real values there, or I can write it in function notation, remembering this first one, this first R is the domain. In our case, that is finding the rules of an inverse function. The last example I want to look at is a little bit different. It's where instead of asking you to find the rule, they want you to find the condition so that it exists, or the largest possible domain. So in this case, we've been given a quadratic, -2, bracket x plus 1 squared plus 5, that is a quadratic that is upside down because of the -2. And they've told us the domain at the end, but they haven't told us the value of a. And we have to find the smallest or least value of a so that an inverse function exists. Remember, for an inverse function to exist, we must make sure that the graph remains 1 to 1. Now I quickly draw this graph. We know the turning point is -1, 5. Remember, it's -1, 5 because, maybe to try my pen. We'll have to do with that. -1, 5 like that. Because you solve this equal to 0 and you get -1, and then the turning point for the y value there. And it's upside down because of that -2. We're doing this. That's our graph. There's something like that. Now it's telling us we want the domain up to infinity, which is this right-hand end here, all the way down, and we're going to stop somewhere. And we need to stop as soon as the graph starts becoming more than one value of x for the value for y. So as soon as it becomes not 1 to 1 or many to 1. Well, if I have a journey along here, all these points along here, if I draw a horizontal line, all those, coming from the left to from the right to the left, it all touches once. But once I pass this turning point, notice what happens. I'm getting another set of lines over here, so I could extend that line out And the horizontal line test is now going to fail every time, isn't it? So with a quadratic, where are you going to cut it? You're going to cut it at the turning point. So the turning point of a quadratic is, whoops, -1,5. Therefore, the least value of a that makes this work is -1. I could have other values of a as long as they're over here. I could have had a equals 1 or a equals 2 or whatever it might be. That's completely out of scale. I could have other values of a to make it work, but the question specifically asks for the least value of a, which means I have to go as far left as I can, and the furthest I can go is that turning point. That is how we restrict a function to make sure it has an inverse. Hopefully you found that interesting and useful. Let me know in the comments if it was no good, I guess, or if it's good too. And enjoy your evenings.